Okay, there's homework due today. It's only 2 problems. I'm gonna push it off until Monday because I think I put on the website just this morning that problems 3 and 4 from the same homework assignment are due Monday. So just hold on to them just so I don't have too many things to keep track of at once. I'm happy to answer questions on them after class if you want to talk about those problems. At least one of them was similar to an exercise we did in the middle of class, looking at a picture of a probability density function and trying to figure out what n, l, and m could be constrained to be. And today our goal is to, as much as possible, continue and maybe even finish talking about orbital angular momentum, which we were in the middle of at sort of a place where we still don't know that much about it, but hopefully everything will kind of clear up by the end, but we're still at this confusing point now where we defined these operators L plus and L minus. Maybe I should roll back to where the definition of L plus and L minus is. L plus is nothing but Lx plus ILy, and L minus is Lx minus ILy. So they're 2 separate operators. Why we would define them that way is not clear at this point. But along the way to showing why they're useful, we proved these 2 commutation relations in the context of a worksheet that we haven't finished yet, but we did that part of the worksheet. And then we went through this proof just briefly at the end of class, showing the following result. If we've got an eigenfunction of L squared, and we assume we know its eigenvalue is lambda, and an eigenfunction of Lz with eigenvalue mu, then we can get new eigenfunctions. So just like for the case of the harmonic oscillator, how we started out with one definite energy state, here we're talking about a state of definite angular momentum, a state of definite L squared value and Lz value. In other words, it's an eigenfunction. We can think of it as a function of r, theta, and phi. It's going to be a 3-dimensional kind of function, just like those hydrogen definite energy states are. This is not a definite energy state, but we're talking about a state of definite L squared and Lz simultaneously. And we found that the theorem we proved said that if you apply L plus to F, then we get another state of definite L squared, and we assumed the L squared eigenvalue was lambda and the Lz eigenvalue was mu. We get another state of definite L squared and Lz. Lambda stays the same, but mu goes up by h bar. The z component of the angular momentum increases by h bar. And if we apply L minus to F, we get another state of definite L squared and Lz. Again, the L squared eigenvalue stays the same, but the Lz eigenvalues decrease. So just like before, the beauty of the algebraic solution is you start with one state and you can generate a whole, what we call a ladder of states from it. And that's very efficient. Much more efficient a lot of times than solving differential equations. And sorry, I see that the camera is unfocused, but hopefully that's better for Alvis and Gracie. Okay, so let's go back to where we were here. That was the importance of that. I think I already answered this question, but I tried to work in some reading responses because more people responded on section 4.3. I'm having a hard time understanding the difference between the L plus minus and L minus plus. And the idea is, L plus minus is not one operator, but it's two operators. There's an L plus operator and there's an L minus operator, and they're defined as Lx plus or minus I Ly. So whenever you see a double subscript like this, there's always an upper one and a lower one, and this means we're doing two different definitions at once, right? When you choose the upper subscript here, you should use the upper symbol over here. And if there's a whole bunch of symbols in there, then we just keep using them that same way. So we don't, at some point that we're about to encounter, we encounter these two things, and all they mean is, it could be L plus or L minus, and it just depends on which one we're choosing. And I'll show you why that's the case. But it isn't one operator, it's two different operators defined in one step. Okay, here again is that picture where we've got our ladder of states. If I can find one state, and I assume I know its eigenvalue of Lz and its eigenvalue of L squared, where again, at this point, those are just being called lambda and mu, then I can find lots of different states which seem to be eigenvalues of L squared and Lz too. And as you apply L plus more and more times, the mu value gets incremented by multiples of h bar, or decremented by multiples of h bar if you apply L minus, whereas the L squared eigenvalue stays the same. So we call that a ladder of states. Now there's a problem here, and that is that L squared and Lz are related. The very definition of L squared was the following. We defined L squared as an operator as Lx squared. That means you take the operator Lx and you apply it twice in a row to whatever it's operating on, right? Plus Ly squared plus Lz squared. And if we keep going up, L squared's eigenvalue, in other words, the definite value of L squared, is going to stay the same, but Lz is going to get bigger and bigger. So if I keep getting states that have higher and higher definite values of Lz, furthermore, this, Lz is, all of these operators are Hermitian operators, so they have real eigenvalues, and that means when I square a real eigenvalue, I get a positive value. And if I keep going up and up and up, this value is going to get bigger and bigger and bigger, and in fact, it will get bigger than this. And so there's some sort of contradiction there where Lz is going to be bigger than the magnitude of L, if you think in terms of the corresponding eigenvalues. So that can't keep going on forever. At some point, L squared would be bigger than Lz, and that's impossible. So we are going to assume that there must be some top rung to the ladder, and which is defined by, if you try to go up one, you get the zero function. Okay, and what that means is it's still, if we apply L plus to this top function, we still get a multiple of the top function, but the multiple would be the zero multiple, and therefore it can't, the new function we get from it is not an allowed eigenvector or eigenfunction. So even though it still satisfies L plus on f top is a multiple of f top, that multiple is a zero multiple, which isn't an allowed eigenfunction. So still satisfies the same property, but in kind of a trivial way. Okay, there's got to be a top rung, and that's, if you like, a differential equation. We're not going to worry about that differential equation. Later on, we're going to see what this particular operator corresponds to in terms of derivatives with respect to r, theta, and phi, and this could be a differential equation. But for right now, let's just note that. Okay, so let's imagine that if we're on the top rung, the eigenvalue on the top rung up there, we're going up by factors of h bar, so it's some multiple of h bar. No assumption about what that multiple is. We're going to call it L. So we're going to say there's some top rung. The state corresponding to it is going to have a subscript of t. Still on the same ladder, so its L squared eigenvalue is lambda. but its LZ eigenvalue is some L multiple of H bar. Now, why L? We're going to find out that the L is exactly the same quantum number L that we introduced in separation of variables for the hydrogen atom. So we're going to have deja vu all over again, looking at this, and find out we're going to get the same differential equations we got in separation of variables. And so we're really doing the same thing. But for right now, maybe it's just a mystery. Griffiths happened to choose script L. It happens to be the same symbol, but no definite relation at this point. In any case, it's some multiple of H bar, because we're keep going up by adding H bar and adding H bar. It's going to be some multiple of H bar. Here, I think, was the source of that reading response question. You see this confusing symbol here. L plus minus times L minus plus as an operator. Well, what that means is I can either have L plus followed by L minus, or I can have L minus followed by L plus. Which one I want depends on whether I'm choosing the upper item or the lower item. If I'm choosing the upper one, if I want a relationship for that, I have to choose the upper symbols here, right? So I get a plus there and a minus there. Okay, so this is just the definition of L plus or minus. This is the definition of L minus or plus, which is the same thing, but with the plus or minus switched in their positions. And you can FOIL it out or distribute everything. Okay, when you do that, you get what in the cross terms, the ones that have an I, the outer and the inner, when you put those together, you get something that looks like the commutator between Lx and Ly. And we know something about the commutator between Lx and Ly from one of the first things we did was work out those commutation relations. It's IH bar times Lz. So therefore, if we set this equal to L plus minus times L minus plus and solve for L squared, okay, so this is a simplified version here. If you look at this equation, solve for L squared, put this other stuff on the left-hand side. Here's a way to rewrite L squared. Wow, that looks complicated. Doesn't look like we're making any great progress, but that's going to help us in just a second. So looking at the worksheet that we were working on last time, I think it says angular momentum at the top. I have one more copy. Is anybody missing theirs? Problem 3 says, suppose we have checked that this identity is true. Use it to show that if we are on a ladder of definite angular momentum states, in other words, we're on that ladder with a maximum LZ value of L times H bar, then we can express L squared for this ladder in terms of L. And the L squared, we're just going to get by replacing L squared with this big mess that's at the top of that problem. So try to chip away at L squared as an operator applied to F top. And we're going to rewrite that as L. Well, I'll let you think about it, but maybe this hint will get you going in the right way. I can simplify my life if I choose the version of that. You know, we had two versions of the identity, one that had a plus first and another one that had a minus first, another one had a minus first and then a plus second. We're going to choose the one that has the minus first and the plus second. I think that was the lower subscripts in the version, at least the version that's printed in your worksheet. So we're choosing the lower selections there. Plus LZ squared as an operator. And then we're choosing the lower subscript, so we get a plus H bar LZ. Okay. And we're going to let this be applied to that top state. Why, to make my life easy, did I choose this version of that identity and not the one with the plus first and the minus second? Can anybody see what? Yeah, because we're assuming the defining thing about L plus applied to F top gives 0. And so this first term is just going to go away because the L plus hits the F top first. If I hit it with an L minus first, it would go down and then it would go back up. But in this case, it gives 0. So simplify what this is. Okay, again, using the fact that L plus applied to F top is 0. The only thing that I have to do is apply LZ squared twice, and each time I apply it, I get L times H bar times the same thing back again, and then when it hits it again, it gets another factor of L times H bar back again, right? And then in the second term, I've got an H bar sitting around, and then when I hit LZ on F top, I get LH bar times F top back again. Okay, and let's just simplify that. Of course, I'm going to factor the F top out on the right-hand side. And what's left in here? Well, I have a factor of L in each of these terms. I've got a factor of H bar squared in each of these terms. So maybe I'll factor the H bar squared out here. I'll factor the L out there. Common factor of L and a common factor of H bar squared. And then I've got another factor of L here and nothing left over there. So that's a +1. So that means if we're on this ladder and there's a top rung such that we apply L plus to the top rung and get 0, then that, and we're assuming the LZ eigenvalue is L times H bar, then the L squared eigenvalue is L times L plus 1 H bar squared, which should hopefully ring a bell from modern physics. You saw that combination, or in other words, the L value, if we think of just the square root of this, is the square root of L times L plus 1 times H bar. Okay, but a lot of times we just leave it in terms of the L squared eigenvalue. Okay, so we've now found that if we know what that highest LZ eigenvalue is, we automatically know which ladder we're on, right? Because the L value determines the ladder. We'll picture those in just a second. Any questions on that before we move on? All of these things are little technical results, but I want to go through them because otherwise, you know, it's too easy to kind of just rush through the stuff in the book and miss all the details. So that no one step is too bad as long as you're willing to use the things that have been proved so far. Okay, so we just found out that the eigenvalue for L squared, which formerly we were calling lambda, now we can rename it in terms of that symbol script L. Okay, so here's what we found out so far. There's got to be a top rung, and we're going to define the eigenvalue for the top rung to be LH bar, the LZ eigenvalue to be LH bar. And if that's the case, then the L squared eigenvalue is L times L plus 1 times H bar squared. There's a similar argument for the bottom rung, right? There's got to be a point where if I keep going down and making LZ smaller and smaller and smaller, then LZ is going to be, you know, more negative than the L squared would allow it to be. And therefore, there's also got to be a bottom rung state such that when I apply L minus to it and I get 0. Okay, so we're going to say, I'm following Griffith's notation here. Let's define, if you're in the bottom state and you apply LZ to it, let's suppose you get some value L bar times H bar, or L with a bar over the top of it, right? No assumption about how L bar relates to L. It's just a different symbol. Now, at this point, if you're following along in the notes, I noticed there was a typo when I was making these slides. What this means is that if you follow that same logic from here and do the same kind of thing, but actually use, instead of using L minus L plus, we're going to use the L plus L minus result in this case. You can show that in that case, lambda has to be related to L bar by lambda is equal to L times L minus 1 times H bar squared. Now we're on the same ladder, and so those two lambda values are the same. We found out that lambda should be L times L plus 1 times H bar squared, and it also has to be equal to L bar times L bar minus 1 times H bar squared. So let's set them equal to each other. And again, this thing I've circled in green, I had a plus sign there, but it's supposed to be a negative sign in the notes. Okay, everything that followed looked like it was all correct, but I had just written something down incorrectly there. So it has to be true that the lambda value is the same on all rungs of the ladder, and therefore L times L plus 1 has to be the same thing as L bar times L bar minus 1. And let's expand those out and see what the conclusion is. So let's multiply them out, put them all on one side and set it equal to 0. Let's do some factoring right here. I've got a difference of 2 squareds. Difference of 2 squared, so that's L bar plus L times L bar minus L. And then I've got minus L bar plus L. And notice I've got a factor of L bar plus L in both of these terms, so I can factor it out. L bar plus L times L bar minus L minus 1. So the product of two things equaling 0, that means the one has to be 0 or the other one has to be 0, right? That's one of our favorite algebraic things to do from way back when. If you got a product of things equaling 0, either L bar is equal to minus L, or L bar is equal to L plus 1. But notice, since we're talking about the bottom rung and the top rung, and L bar represents, or L bar times H bar is the LZ value at the bottom rung, L bar has got to be less than L. And so if L bar is L plus 1, that doesn't make any sense because L bar is less than L. It can't be 1 greater than it. So that solution can't be true, and therefore it has to be true that L bar is minus L. Okay, and so that means that if you're on the bottom rung, the LZ eigenvalue is minus L H bar for the bottom rung. It's plus L H bar on the top rung. Okay, and you go up by multiples of 8, or you go up by H bar every time you go up 1 on the rung. So I start at minus L H bar, and then I go to minus L plus 1 times H bar, and all the way up until I get to L by integer increments. And so the allowed values of LZ are multiples of H bar, where the multiples have to be between minus L and L. I know it's not the most exciting result, but it's sort of narrowing down. You're kind of seeing, since we're not solving partial differential equations, we don't have a lot of concrete stuff to work with, but we do have to do these algebraic kinds of manipulations, and they're easier than solving differential equations. Okay, here's a voting question. Maybe you know the answer from your previous work. We just showed that if we're on a certain ladder, the eigenvalues of LZ on that ladder are multiples of H bar, where the multiples go from minus L up to L in integer steps, right? Those are what we're calling the M value. And we'll show that those are the same M's that we got before. Right now, they seem to be totally unrelated, even though it's looking rather familiar. What then can we conclude? If you're going to step up from minus L up to L by integers, and not miss the top one, right? That's somewhat restrictive, right? I got to start at a negative number and end up at the corresponding positive number by stepping up by integers. I can't do that starting at minus pi. I won't end up at plus pi, right? By stepping up by integers. What does that tell us about the allowed values of that quantum number L? What are they restricted to? And some of these are missing numbers compared to other ones. So if it's missing a number, we're going to consider it wrong. You have to give the complete set of allowed L values. Let's see a quick vote. I mean, either you're going to get this one or you're not. I'm not seeing anyone voting for the correct answer. The correct answer, oh, I hate it when the correct answer is none of the above.
Oh, dear.
But you may remember this from earlier, either the reading or from modern physics, that if I've got a step from a negative number to the corresponding positive number by integers, the restriction is that either L has to be an integer, or it suffices to use only the non-negative integers here, because we're going from minus L up to L. So L is a positive number that we're ending up on here. So it either has to be a positive integer, or I guess a non-negative integer, or what we would call a half of an odd integer. That's like 3/2 or 1/2 or something like that, right? That's because, remember that the requirement that we found out is that I've got to be able to step from a negative number to the corresponding positive number going up by integers. And again, that's very restrictive. If you start at minus pi, you're not going to end up at plus pi if you step up by integers. Or it may be an easier case to think of is if I start at minus 0.2, and then the next one is going to be minus 0.2 plus 1, which is plus 0.8. I've already missed the corresponding, so it doesn't work very often. It's got to be a very particular value. And of course, integer values of L and non-negative integer values of L all work. If I start at minus 3, minus 2, minus 1, 0, 1, 2, 3, got it. Ended up on the corresponding positive one. But it's also true that if I start out at if L is a half odd integer, in other words, I start out at minus L, and minus L is minus 3/2. If I go up by 1, then I'm at minus 1/2. If I go up by 1 again, then I'm at plus 1/2. And if I go up by 1 again, then I'm at 3/2. And I've gotten to the corresponding positive one. So it looks like half odd integers work in addition to integers. So in general, that means every half integer will work. And since we're taking L to be non-negative, we mean the non-negative half integer ones. So any n over 2 will work, but when n is even, right there, if n is even, then n over 2 is still an integer. So, but the interesting ones that you probably weren't thinking of were the half odd integers. Okay. So therefore, to summarize everything we found out from this algebraic kind of method, using our L plus and L minus and using that theorem that we proved, that actually no step is very hard to do. It's just when you put them all together, it's somewhat, you see this thing in the box here and you're like, oh, I remember that. Yeah, but where did it come from? Man, that's hard to remember. But we've been through every step essentially here. Maybe we didn't check a few technical results that are actually pretty easy to prove. So we found some eigenvalues that correspond to some eigenfunctions. We still don't know anything about the eigenfunctions, but we do know the quantum numbers they depend on. They depend on an L and an M, right? The L tells us about the eigenvalue of L squared. So these functions that we still don't know anything about are eigenfunctions of L squared and LZ, both at the same time. L squared applied to one of those gives L times L plus 1 times H bar squared. That's what we showed a little bit earlier. And LZ applied to that is M times H bar. L can be any non-negative integer or half odd integer. and m has to go from minus L to L in integer steps. Whew. Okay, so that's something that hopefully at least rings a bell from modern physics. You talked about this stuff, I'm assuming, about angular momentum in modern physics. Easy to forget, but usually it comes back pretty easily too. Okay, so that means that if we choose a particular value of L squared, in other words, we choose what script L is, then we can form a ladder by going from the minimum LZ value up to the maximum LZ value. So for example, if I choose L equals 0, the ladder isn't very exciting because when L is equal to 0, m has to go from minus 0 to 0. So 0 is the only allowed value for m. So there's only one rung on the ladder. There's one state, which we would label as F. This is LM. Lower subscript is L there. And so both L and M have to be 0. There's only one rung on the ladder. If you apply L plus or L minus to it, you get 0 in both directions. L equals 1/2 is the next one, right? And there we're saying L equals 1/2 applies to both these functions, but we have one with m equals minus 1/2 and m equals plus 1/2, stepping up by integers. For L equals 1, we have 3 states, all the same L, but different m values. For L equals 3/2, all the same L, but different m sub L values. Here's a picture you saw in Griffiths. It's displaying the same information the same way. This is a picture corresponding to L equals 2. So when L equals 2, I would expect my m sub L's to be minus 2 h bar, minus 1, 0, 1, and 2. So there's 5 different LZ states. And in this case, we would say L squared, the value of L squared is 2 times 2 plus 1 times h bar squared, and therefore the value of L is the square root of that. The square root of 2 times 2 plus 1. So the square root of 6 times h bar, which is a little bit bigger than 2 h bar, 2.45 approximately h bar. In this case, and this is always true in these cases, the momentum never points exactly along the z direction. In other words, the z momentum in this case is at most 2 h bar, but the total angular momentum is 2.45 h bar. And so the z momentum is always a little bit less than the total angular momentum. And we display that, in this particular picture, we're drawing each of the levels as kind of a circle centered on the z-axis, which there's actually a lot of information in that circle. So we're saying here there are 5 different circles that we're drawing. This one corresponds to LZ equals minus 2 h bar, right? The L vector is pointing somewhere on this circle, so it has a definite LZ value because its projection onto the z-axis is definite. If the arrowhead points from the origin down to anywhere on this circle, then the projection onto the z-axis is definite. And in any of those cases, the value of LZ is going to be less than in magnitude than L. So we're never going to know L exactly, even though we're never going to be able to align L, the total angular momentum vector, with the LZ direction, because if we did, if L were exactly aligned with LZ, in other words, if LZ equaled the magnitude of L, then we would know that both Lx and Ly had to be 0. We would know all 3 values of Lx, Ly, and Lz simultaneously, and that's not allowed because they don't commute with each other. We can't find states that have definite values of all 3 of those at the same time. So Griffith says something like this, and it's a good little paragraph, and it reminds us, I don't know what happened with my symbol there. I'll have to think about what that symbol is. But just like there in quantum mechanics, we don't say, oh, you can know position and momentum, and those are 2 things that you can know. No, you can't know position and momentum. The more you know about position, the less you know about momentum. And so there's not really 2 things to understand. you can either know a lot about position and very little about momentum, or vice versa. It's the same way here with Lx, Ly, and Lz. Griffiths says something to the effect that there aren't three components of angular momentum to know in this case. There is a single state, which is some linear combination of all of these. And if you know Lx definitely, then you don't know Ly or Lz definitely. There's some uncertainty to them. And you can kind of see here from these circles, they're trying to display that as Lz gets bigger, the radius of the circle gets smaller, which means there's less uncertainty in Lx and Ly, right? Here's the Ly axis, here's the Lx axis. So as Lz gets to the top rung, there's less uncertainty in Lx and Ly, but there's always uncertainty in Lx and Ly. And also Griffiths mentions that for macroscopic systems, this doesn't seem to make sense. Here, for macroscopic systems, the angular momentum is going to be huge compared to h bar. I remember what the symbol is. It's a much, much greater than symbol. The angular momentum, if I take a top and spin it, right? And it's spinning here on the table. Let's imagine it's not precessing or nutating or anything like that. We spin a top and it's just spinning in space. The angular, h bar is a tiny amount of angular momentum. The angular momentum of the top is going to be huge compared to h bar, okay? And so that means script L has to be huge. That quantum number is large. And when the quantum number is large, the square root of L times L plus 1, that's the square root of L squared plus L, I can ignore the L compared to the L squared when L is large. And so the magnitude of the total angular momentum can be really, really close to the Z component of the angular momentum in that case. And so we don't notice the discrepancy between not knowing, if we're in a definite LZ state, we don't necessarily ever know its projection. I guess I'm saying that, I was tempted to say it the wrong way. If we are in a state of definite LZ, we can never have it align with our Z axis exactly, because that would involve knowing Lx and Ly. But in principle here, or in practice, if we have something macroscopic, these numbers are so large that we can effectively line it as close as we'll ever notice with any axis we choose. Okay, and again, if you look at this diagram, that just repays careful thinking about. It works in a lot of different ways. On this circle, L squared and Lz are certain. L squared is the value, L squared is the same everywhere on this circle because, on a sphere, because a sphere is defined by L squared equals a constant, right? The magnitude of R is a constant, right? And Lz is certain if you're on one of these circles, right? Because your Z projection is the same no matter where you are on that circle. But Lx and Ly are uncertain, but it's also true that you do know Lx squared plus Ly squared, because L squared is certain and Lz squared is certain, and therefore Lx squared plus Ly squared is certain. That's amounting to saying that you're on this circle, because everywhere on the circle has the same value of Lx squared plus Ly squared. So it's kind of a neat picture, even though maybe when you look at it, you don't get all that information out immediately. Here's another reading response question. The axis of a spinning top will point in the direction of its angular momentum, the Z-axis. The more angular momentum the top has, the less its rotational axis will deviate from the Z-axis, but will never perfectly line up. Is this analogous to how we think about how L is less than the square root of L times L plus 1? I would say no in this case. We're imagining, I think, a top in classical mechanics. And in classical mechanics, if we have a completely symmetric top, the usual kind of thing where you have a disk of material and you've got something that you can hold with your hand and something coming out the bottom, we can actually set it spinning in such a way that, of course, its angular momentum vector is going to be along the axis that it's spinning on, and we can have its rotational axis be that direction too. There's nothing contradictory about having a top spinning straight up, and so that would be the case where hey, I know the value of L and I know the value of else Z, and the value of else Z is the same thing as the value of L in this case. So there's nothing related in that case, I think, between the question that was being asked and the quantum case. All right, let me pause before we transition to another topic in angular momentum operators, and that is, we found out a lot about the eigenvalues, right? We found out what these quantum numbers are, but we still don't know necessarily what the eigenfunctions are at all. And we're thinking of the eigenfunctions as functions of r, theta, and phi. They're like good old eigenfunctions. We found eigenfunctions of energy for the hydrogen atom. We ought to be able to find the eigenfunctions of these operators. Okay, so we know everything we want to know about the eigenvalues that can happen. What about the eigenfunctions? As explicit functions, we're going to do them in spherical coordinates. You can't do that by purely algebraic means. We need to actually solve a differential equation, right? We said the algebraic solution is great. If you know one state of definite LZ, you can get all the other states of definite LZ from the algebraic solution. But you can't find one state without going to a differential equation. So it's similar to the case of a harmonic oscillator, where we said we wanted the states of definite energy. We found if we knew one state, psi 0, we could get psi 1, psi 2, psi 3 going up. But the only way to find out the explicit expression for psi 0 as a function of x was to write down a differential equation. We said you apply the lowering operator to it, you get 0, and that can be translated into a differential equation. We're going to do the same kind of thing here for the lowering operator. So we need an expression, a differential expression for the angular momentum. And remember, it's r cross p. So we're writing p in terms of del, and p as a vector was minus I h bar del. For whatever reason, the I is in the denominator there instead of a minus I in the numerator. Okay, and so what we're going to do is substitute the expression for del in spherical coordinates, which again, I'm not going to elaborate on here. This isn't too hard to figure out. The Laplacian in spherical coordinates kind of bad to figure out, but here's an expression for del in spherical coordinates. And the expression for r vector, which we're crossing with del here, is just the magnitude of r in the r hat direction. So that's a nice simple thing. And we need to take a cross product between these two. And we're going to do that on another worksheet we're starting now. For Gracie and Alvis, this worksheet is posted under today's date on the website. So take a look for that. We're just doing problem 1. And what I want you to do is calculate h bar over I times r cross del. You have to take the cross product between these two expressions. And the cross product is really concerned about how the vectors operate on the vectors. So you're going to get an r hat cross r hat thing in the first term, an r hat cross theta hat in the second term. You got to think to yourself, wait, what direction is r hat plus theta hat in terms of r hat, theta hat, and phi hat? If you hopefully you remember about those directions, what direction at each point in space does r hat, theta hat, and phi hat point? So simplify that cross product so that no more cross products remain in it after you do that r cross del. Okay, there's not too much work to do beyond what I have written on the board here, but when we take the cross product, of course, it's those unit vectors, as long as we keep them out in front of, you got to be careful. You can't just move these through the derivatives because r hat is a function of theta, right? As I change theta, the vector r hat changes. So I have to make sure if all these are out in front of the derivatives, I have to keep them out in front of the derivatives. I can't move them over there because these things depend on theta, right? R hat, which points away from the origin, depends on theta. Theta hat depends on theta as you go around. So it's a little bit confusing, but keeping everything in the same order, so the derivatives appear second, as they do in when I'm doing r cross del. The cross products just happen between those unit vectors. And what's r hat cross r hat?
Oh, that's 0.
That's 0. The cross product between any vector and itself is 0. What about r hat cross theta hat? Phi hat. Yeah, if you look at, I'm reminding you on there the directions of r hat always points in the direction of increasing r at every point in space. Theta hat points in the direction of increasing theta, so it points kind of in this direction. And phi hat always points around in the direction of increasing phi. So if the origin is, where, at my armpit there, r hat cross theta hat gives me a vector in the phi hat direction. So this is phi hat. And what about r hat cross phi hat? Yeah, it's actually negative theta hat. You kind of got to stare at that diagram that I provided to the right in that problem. But let's just draw a little picture maybe to convince you of that. Here's the x-axis, here's the z-axis. Here's a point in space, a randomly chosen point in space. At that point in space, r hat is a unit vector pointing away from the origin, right? Theta hat points in the direction of increasing theta, and phi hat points around in that direction. It goes from the plus x towards the plus y axis, which is actually into the board. So I guess if I were to use that convention where that's an axis going into the board, that would be the plus y direction. So the plus y direction is going into the board. And therefore, the phi hat vector at this point in space goes into the board. So if I do r hat cross phi hat, I get a vector in that direction, which is in the minus theta hat direction. Because they're both unit vectors, I get a unit vector out. Okay, so if we simplify this, we get h bar over I phi hat dd theta minus theta hat over sine theta dd phi. Okay, that's not as bad as it could be here. So let's just take that at face value. Okay, there's our expression. And now the next step is we're going to want LZ, because we're going to write down, something about, at least on the surface of it, it seems like we would want to get the L plus and L minus operators and be able to require that L minus on the lowest rung gives 0, and that would be a partial differential equation. So I need to know something about how to write LZ. Now I've got the full L here. I've got the full L expression. I just want the Z component. Unfortunately, it's written in spherical basis elements. So I need to write phi hat in terms of x hat, y hat, and z hat. And I need to write theta hat in terms of x hat, y hat, and z hat. And then we're going to be interested in just pulling off the z hat component of that. So I don't, for whatever reason, I was using I hat, j hat, and k hat, but you could write x hat, y hat, and z hat just as well. I tend to use those nowadays. Worksheet problem 2 is saying write out what phi hat is in terms of I hat, j hat, and k hat, and what theta hat is in terms of I hat, j hat, and k hat. And you might have to stare at this diagram. So I'm going to just give you a minute to think about it, and then we'll do it together to figure out how to visualize that. It does perhaps tax your visualization skills, but it's something that comes up a lot in physics, translating between spherical unit vectors and Cartesian unit vectors. Here we've got spherical unit vectors, and we want to express them in terms of x hat, y hat, and z hat. Again, I'm not sure which books you've used. Sometimes people use I hat, j hat, k hat. They just mean x hat, y hat, z hat. So for whatever reason, I wrote out this worksheet in terms of I hat, j hat, k hat. But you can translate if you feel better about that. Okay, what's the answer to A? What is the k hat or z hat component of phi hat?
R divided by k times cosine phi, if I'm envisioning this correctly.
Yeah, that may be true, but there's a much simpler answer.
Oh.
If I think of phi hat, let me go off of here just so I can point in space. Phi hat at every point in space points in the direction of increasing phi, so it points around this way. Z hat's in this direction. So what is the z hat component? No matter where I am in space, this points around in a circle. That's the phi hat vector as I'm circling around the z axis where my body is, right? So what's the z hat component of a vector that looks like this? It's 0, right? It's not till it's lying parallel to the xy plane. Right, so the answer to A is 0. It doesn't have, or it has only the 0 z hat component, and therefore it lies in the xy plane. And I can use that to my advantage to answer B, because now I know that phi hat lies all in the xy plane. I can just draw a view down from the z direction onto the xy plane, and I know my full vector phi hat will lie in there. So let's try to do that and imagine what it would look like. Here I am looking down from the z direction. Here's the x-axis. Here's the y-axis. X hat cross y hat is z hat. So my z hat's going to be coming out of the board here. There's my coordinate system. We're looking down from the positive z direction. And here we are at some point in space. And the very definition of phi is, that point in space may actually be out here, but the definition of phi is how far do you have to swing from the plus x hat direction towards the plus y hat direction? That's what phi means. You can see that displayed in 3D in the diagram there, right? So we're looking down the xy plane, and the phi hat vector is perpendicular to that line I've just drawn. It's a unit vector pointing in that direction. And maybe I better draw it a little bit longer. It's a unit vector, but I'm going to draw it as if length, well, sorry, that's phi hat I'm drawing there. And I want to know, we already know its z hat component is 0, and now the only question we have is what is the x hat and y hat component? And I can see that just by saying, oh, the x hat component and the y hat component will be at least the magnitude of those will be the sides of the lengths of this right triangle. And then I can put in the minus signs or the plus signs as needed. It looks like phi hat's y component. So let's start writing out what phi hat is. Phi hat is 0 z hat. That's what we found out in A. What goes in front of the x hat here? Well, let's see. If this angle is phi, is everybody willing to believe that this angle here is phi that I've drawn in there, right? Because as this angle closes to 0, this one will close to 0 in the same way up there. So that angle is phi. This vector is a unit vector. It's phi hat, so it has length 1. So the hypotenuse is length 1. If I want to find the x component, that's either this side or this side. First of all, it's a negative x component. And its magnitude is 1 times the sine of phi to get to this side, or to get to this side down there. 1 times the sine of phi. And similarly, to get the y hat component, it's just going to be 1 times the cosine of phi with a plus sign in front. Okay, so that's how to write phi hat in terms of x hat, y hat, and z hat. Again, why are we doing this? Because we want an expression for LZ as a differential operator. And so we're just going to pull off the z component after we're done doing all this stuff. That's just phi hat. Now we got to do theta. Okay, let's think about how we can draw a picture for theta. Maybe I'll go down here, maybe erase this later. If we draw the plane that contains both the vector that's pointing from the origin to the point P and the z hat direction, in other words, if I draw the plane where z hat is pointing straight up, here's the origin, and I'm going to make that point that we're talking about actually lie in the plane that I'm drawing. So here's the distance we're calling r. Here's the vector r hat going in that direction. We're concerned with theta hat, right? Theta hat points in this direction. Okay, this direction's neither x hat nor y hat, but it's a direction that's lying along this diagonal dashed line in the bottom. Where this angle here is theta, right? Theta is how far off the z-axis that point is that we're talking about in space, right? So that's the angle theta. If that angle is theta, hopefully you'll grant me that this angle is theta in there. And so I'm going to draw a little right triangle here that has the angle theta in it. And that's, you know, again, this is a unit vector, so its length is 1. The hypotenuse length is 1. That means the x hat component, well, okay. We're not asked about that here. In C, we want to know what is the k hat component of theta hat. The k hat or the z hat component is going to have magnitude this size, and it's going to have a minus sign in front of it because it's going down, right? So we're expanding theta hat, and we're going to find out what its z hat component is. And it looks like it has a non-zero z hat component, which is 1 times the sine of theta to get to this side with a minus sign in front of it. And I'm feeling like the class is over, and amazingly, it's exactly 1:40. Well, okay, so what do we do to finish this? I'm probably not going to start in the middle of this next time, but what do you do? Well, then what we do is this vector theta hat, I can project it onto the xy plane down here. And we just say, well, I know it has a factor, its projection on, if its length is 1, its projection onto the x hat and onto the xy plane has length cosine theta. So here's a vector of length cosine theta, and then I have to further project that onto the x hat and y hat axes in a projection on the xy plane. And the final answer is you get cosine theta times the cosine of phi x hat plus cosine theta sine phi y hat. That one requires a little bit more thought and careful projections to be able to do the geometry and get those numbers. But it's a useful skill to be able to draw these diagrams and figure out how to write one set of unit vectors in terms of another set of unit vectors. So now you can see when I do that, I'll be able to, when I substitute back in here for theta hat and phi hat in terms of x hat, y hat, and z hat, I'll be able to figure out what LZ is. I'll just pull off the z hat component of that, and that will give me one of my differential equations.